Hello, students. Welcome back for our next topic in science. And before I even introduce this particular science topic, I just want to show you some stuff, some items. And I want to see if you can tell me what you think these items might have in common with one another. So here we go. I'm going to switch over to the close-up view, and we're going to start with this. You can probably guess what this is. This is a cooking pot. Cooking pot with a handle. So here's your first item, cooking pot with a handle. Next, got a styrofoam cup. Next, we have one of these little fridge magnet thermometers that hang on a fridge or the side of a fish tank, maybe. Let's see, what else? Oh, here's something cool. I have a mood ring. Ooh, let me model that for you. Yes, I just put it on. So it's starting to change colors. My mood ring, I'll leave it on for you. Here is a tile from the space shuttle. Ooh, look at that. Space shuttle tile. Here, I'll even open it up and show you. It's kind of fragile. This is an actual tile that was on the space shuttle. I got it from NASA. Pretty cool, pretty cool. Oh, by the way, my mood is improving. It's getting more blue. All right, let me show you this now. What in the world is this? Let's see, can you see this? Yeah, this is pretty cool. This is pretty cool. I am going to put my hand around this globe, and I want you to watch what happens. Ready? Look at that. Whee! I hope you could see that. That was pretty cool. How about I switch sides now? I'm going to hold it with this hand and let go on this side. Whee! Check it out. This is called a hand boiler. I'm boiling water with my hand. How cool is that? All right, next. I've got here a lab grade thermometer, my friendly thermometer. And finally, oh wait, I got something else here. Yeah. Woo! Look at this. That's a lab grade thermometer. This is just a downright cool thermometer. Look at that. Can you see that? Maybe you've seen these before. Temperature according to this thermometer in the lab right now is 74 degrees Fahrenheit. 74 degrees Fahrenheit. By the way, it might be the last time you hear that word being used this week. Fahrenheit. Well, we'll talk about it again. But one more item. One more item. This one here. Can you see this one? Are you ready? Yeah. So I have just shown you a number of items. And my question to you simply is this. What do all of these items have in common with one another? Take a moment and discuss that now. Perhaps you came up with the commonality between all of the items. And by the way, my mood ring is nice and blue now. And that is they all have something to do with heat energy. Heat energy. And that is our topic this week, heat energy. And we are going to be discussing the question here, well, what is heat? In fact, take a moment right now and talk about what do you think heat is? What is heat? Well, from a scientific point of view, heat is the energy involved in the internal motion of particles. And while you're writing that down, I'm going to try desperately to take my mood ring off because it's stuck on my pinky finger. So while I take off my now blue mood ring off, you can write this down, that heat, all right, I got it. Heat is the energy involved in the internal motion of particles. Now, as you can see, I've bolded and italicized certain words to emphasize them. Heat is a form of energy, as you know from the last topic. And this internal motion, if it were possible for us to put our magic glasses on and be able to see the world on a molecular level and look at an object and see how the particles, the molecules themselves are moving within that substance, we would see that the hotter something is, the faster the molecules are moving around, because heat energy involves the internal motion of particles. The slower the particles, the less heat energy there is. The faster the molecules, the hotter something is. So when we use a device like this hand boiler, it's also could be called the heatometer. The hotter you are, the more bubbling is going to happen. So you can see pretty clearly here that I must be pretty hot. I must be pretty hot in order to make the water boil. Now, normally I'd pass this around and see who the hottest person is in the classroom, but for now, you're just going to have to take my word for it that I am the hottest person in the class right now. Woo! Look at that water bubble. Yeah, check it out. Woo! The heat energy coming out of my body is incredible. All right, so let's talk about this heat energy a little bit more. There's some very important concept here that you might remember from last year in 7th grade when we learned about diffusion. Remember diffusion? Diffusion, the movement of substances from high concentration to low concentration. Well, heat energy is very similar to diffusion in that heat energy will always flow like this rubber ducky. If I drop it, whee! The rubber ducky, if I drop it, goes from a high area to a low area. Heat energy always flows the same way. Heat energy always flows from a higher temperature to a lower temperature. Heat will flow as long as one temperature is higher than another, which is why you'd never want to cool down your house by opening a refrigerator, because eventually the temperature will just balance out. But that's a story for another day. The point is, energy moves from high to low, and with heat energy, it moves from hotter places to colder places. Not the other way around. Not the other way around. Heat energy always flows from hot to cold. So if I were to ask you to touch a cold window, maybe some of you have done this, like on the bus or in a car. Do you ever make those little baby feet by using the the backs of your hands on a window that's all foggy? You press this part of your hand on a window, then you use your finger to make little toes. Oh, it's great fun. But if you've ever touched a window in the wintertime, how does it feel? Feels cold, right? Now, from an energy point of view, what's going on? Is your hand getting colder, or is the window getting warmer from your hand? What do you think? Well, from a science point of view, that cold window is getting warmer because the heat energy is getting sucked out of your hand. Because remember, heat energy always goes from hot to cold, from warmer to cooler. So if you touch a cold window, the heat energy is moving from your hot hand to that cold window, not the other way around. There's no such thing. One of my favorite examples is like in the wintertime. Have any of you ever opened up a window or a door and your parents or somebody at home says, "Close that window, you're letting all the cool air in"? How many of you have ever heard that before? It's not true. You are not letting the cold into your home. What's happening is you're letting the heat escape your home. And as a result, your home has less heat energy and the temperature or the heat energy decreases and it feels colder. But you're not letting the cold air in, you're letting the hot air out. Big difference when it comes to heat energy. So let's talk more about this. As I've been stressing, the movement of heat energy is from high energy to low energy. Always, always, always. From hot to cold, just like if we were to take a ball or a ducky, bring it up somewhere high and let it go, it goes down low. Why? Because that's how energy flows, from high concentration to low concentration, and heat is no different. So the movement of heat energy is always from high to low. Now, it doesn't do this in the same way all the time, but it always goes from hot to cold, but it does that in three different distinct ways that we're going to talk about here today. Heat flows in three different ways: conduction, convection, and radiation. So let's talk about these three types of heat transfer, starting with conduction. I gave an example of conduction a moment ago when I asked you about touching a cold window. Because when you touch something like a pot, that might be hot. Golly, all right. Touching something directly is an example of conduction. Heat is conducted through different materials like metals. Metal is a good conductor of heat energy. That's why we use metal to make pots, because pots are made of metal and you want whatever's on the inside of the pot to get hot. So why not use something that conducts heat energy? But putting your hand on a window, putting your hand on a pot, putting your hand on a hot stove, not a smart thing to do, because the conduction of heat energy will go right into you and will cause a burn. Again, not a very smart thing to do. Now, regarding conduction, there are two types of materials. The first one I already mentioned, the metal. The metal pot, for instance, metal is a good conductor of heat energy. By the way, it's also a good conductor of electrical energy. We'll talk about that a little bit later in the year. But conductors are materials that do transfer heat energy well. Metal is just a great example. And by the way, there are different metals that are better or worse conductors than other. Like if we look at this pot, for instance, the top of the pot is made of one kind of metal and the bottom is made of a different kind of metal. There's a reason for that. And the reason has to do with the ability of different kinds of metals to conduct heat energy easier than other metals or other materials. And our lab this week is going to involve testing different metals. And, I won't talk any more about the lab right now, but plant that seed in the back of your mind that our lab activity has something to do with metals, conductivity, and heat energy, to be sure. So conductors do transfer heat energy. By the way, there's 3 spoons here, or 3 different materials. There's a plastic spoon, a metal spoon, and a wooden tongue depressor type thing. You can imagine that it's a wooden spoon. I don't know if any of you have any cooking experience, but if you have a pot that's getting hot because you're making, let's say, pasta for dinner or what have you, don't answer this out loud, but I want you to think about it. Which one of these spoons do you think would be best to leave in the pot while the water's hot so that you get burned not? Think about that for a moment as we continue with our notes. The other type of material when it comes to conducting heat energy is called an insulator. Now, an insulator is a substance that does not transfer heat well. Have you ever had a cup of hot chocolate, for instance? Or I know some of you might drink hot coffee or hot tea, but I prefer hot chocolate. So imagine you had hot chocolate. And you were out on a cold day. What kind of container would you want to put your hot chocolate into so that your hands don't get burned? Would you have it in a metal cup, metal container, or a styrofoam cup? If you don't want your hands getting burned, which cup would you want to use? Styrofoam or metal? Hopefully you said styrofoam, because styrofoam is a good insulator. In fact, if any of you have ever built a home or seen a home being built, maybe you've seen that pink fluffy stuff that's inside your attic, or on the floor of your attic, or between the outside walls and the inside of your home. That pink fluffy stuff is an insulator. It prevents the heat flow into or out of your home, depending upon what season of the year it is. But styrofoam, great insulator. Here's some other materials here: fabric, bubble wrap, paper, foil. Think about which one of these might be better insulators than others. Don't say it out loud, just think about it for now. Oh, and by the way, this hot pots usually, or a pot when it's not so hot, has a handle. Guess what? You're supposed to use the handle when the pot gets hot, because the handle, what do you think the handle is? Regardless of whether it's plastic or wood or some other kind of material, what property do you think a handle has? It would be called a good insulator. If it wasn't a good insulator, you'd get burned. All right, let's talk about number 2. Number 2, the second way that heat can be transferred or moved from one place to another. And the second type is called convection. Convection. Convection is what takes place when heat is transferred through a liquid or a gas. If you were to boil some water up in a pot and you watch it, that water on the bottom of the pot gets heated first, but before too long, the water on the top of the pot will get hot as well. How? Through convection. Convection is how that happens. And you can see, like in a teapot here, or a tea kettle, the hot water will move up as the cooler water flows down, and you get what are called convection currents. Maybe some of you have a convection oven at home that is heated in a similar way, and the airflow in the oven circulates around so that your food can heat up through convection, or the heat energy moving or transferring through the gas of your convection oven. Another example we experience all the time, just going outside or looking out a window, is the weather. Our planet has an atmosphere of various gases. And we have a fairly moderate temperature range here on planet Earth, which is a good thing because it enables us to live here, unlike other planets that have either very little or no atmosphere, or atmospheres so thick that convection can't permeate through the atmosphere well at all. Like Venus, it just stays hot all the time. But on Earth, we have convection currents on a daily basis. We have wind flow because of convection currents. We have a moderate temperature throughout planet Earth or across planet Earth because of convection. We have weather and climate. Climate's more a result of the tilt of the Earth, but we certainly have weather as a result of convection. This room right now is being heated up through convection. There's a heater on one side of the room, and that warm air is moving through the air in the room until it gets to the other side. It's through convection currents. So convection is the second type of heat transfer. That brings us to the third, called radiation. Now, I know when you hear radiation, a lot of people automatically think bad things like, oh, radiation, nuclear bomb, we're going to die of radiation poisoning. Well, we couldn't live without radiation. Radiation is simply, in this context of heat energy, radiation is simply the transfer of heat energy through an empty space, such as the empty space between the sun and the earth. It's a vacuum, the vacuum of space. There's nothing there. Radiation, the transfer of heat energy through empty space or a vacuum, doesn't need a solid to go through. Conduction involves touching a solid, and heat transfers from one place to another. Convection, the boiling water, involves a fluid or a gas. Radiation doesn't require any material like that to flow through. Radiation can travel through empty space. Now, if I were to show you this little lighter here, this little light of mine, I'm gonna make it shine. This little light of mine, it's hot, so I'm not going to get too close to it. And I can feel that it's hot, and I'm a good distance away from it, but I can feel the heat. Not because I'm touching it, conduction, not because the heat energy is moving through the air. Actually, that heat energy is moving up. That's convection. But I'm feeling the heat right now, even though my hand is below the flame, because of radiation. Radiation, the transfer or movement of heat through empty space, and it happens in all directions. Best example of radiation is how our planet is heated by the sun. The sun, the energy from the sun, the infrared rays from the sun warm up our planet, even though we're 150 million kilometers, 93 million miles away from the sun, and there's absolutely nothing between the sun and us, generally speaking. Yes, I know there's Mercury and Venus, some few asteroids, meteoroids, and things like that. But for the most part, there's nothing between the sun and the earth that allows the heat energy to flow. It flows through the vacuum of space. So here are a couple of examples of how energy flows. Okay, we're just going to finish up a little bit more for today. And I want to ask you the next question here. How is heat measured? How is heat measured? All right, you may have come up with some different ideas of how heat is measured. And I'll tell you what, I'm going to hold you in suspense until tomorrow when we pick this topic up a little bit more. So until tomorrow, I'm going to say bye bye.